Hello and welcome to our next lesson. Today we are looking at applications of sine and cosine law. So by now you should have got lots of practice using sine and cosine law with any given triangle to solve for unknown side lengths and measurements of angles. And now we're looking at some word problems where it is a mix of sine and cosine law. So you do first have to determine for each problem whether it's best to use sine law or cosine law, and also to determine based on the question which values in the triangle are given to you in order for you to solve for the required values as well. So for the first example, a wall is 2.4 meters long and it has started to lean and now makes an angle of 80 degrees with the ground. A 3 meter long board is placed on the ground and leaned against the wall to prevent it from falling. And that's exactly what we see in this diagram here. We have our 2.4 meter wall. It is making an angle of 80 degrees, and we have this 3 meter long board that is helping keep this wall from standing up. And of course, this is not a right angle triangle, so it is one of our acute angles, so we do have to use either sine law or cosine law. So first, what angle does the board make with the ground? And we're asked to round to the nearest degree. So we're looking for this angle that the board makes with the ground. So here we have two side lengths of this triangle that's formed here, and we have this angle. So because I have one of the angles, right away I check, do I have the opposite side length so that I can create a sine law ratio? And yes, I can create that ratio from this 80 degrees and its opposite side length. And because I'm solving for this angle and I have its opposite side length as well, then I can just apply sine law. So from here, and I will have to define this angle here, so let's put that as theta. So let theta be the angle the board makes with the ground. So then, sine of theta over, and again, I use the sign in my numerator because that's the one I'm solving for, over 2.4, which is its opposite side length. And here we have sine of, it's equal to sine of 80 degrees over 3, and these are meter. So then sine of theta is equal to this whole fraction there times 2.4. However, I am solving for theta, so I do need to take the sine inverse. And again, I will do this whole expression there to have an exact value. So then, if I evaluate this, just to double check, I do get 51.98 degrees, but then we are rounding to the nearest degree. So then we have exactly as my concluding statement says here, the board makes an angle of 52 degrees with the ground. And we don't have to solve for the other values here because we're only asked for that angle there. So that would be it for part A. Now, part B asks, what angle does the board make with the wall? And here we're rounding to the nearest degree again. So now we're actually solving for this angle right here. So let me call this angle now alpha, and this is what we're trying to solve. So if I'm analyzing now here, I have two options. I do know these angles, so I can actually solve for this using the sum of the interior angles of the triangle, or I could perhaps use cosine law because I have these two side lengths and, or actually, sorry, no, I wouldn't be able to use cosine law because I don't have this side length. So in fact, I do actually have to just use the sum of the interior angles, which is precisely what I've done here. So 180 degrees minus 80 degrees minus the 52 degrees we found up there is 48 degrees. So I will label these as well. This is now 48 degrees, and this one was 52 degrees. But then, yeah, there we go. Now in part C, we want to know how far is the board from the base of the wall. So we are looking for this side length over here. And so this side length right here. So now I have options here as well. Because I have all the angles, I could use cosine law to solve for this side length because um, let's say this is d. D squared will be equal to 2.4 squared plus 3 squared minus 2 times 2.4 times 3. Um, Cosine of 48 degrees because it's the opposite angle, or because I have the other side lengths, I can also just use sine law, which is what I did here. So let D represent, as I showed on the diagram as well, the distance from the board to the base of the wall. So sine of 80 degrees over 3 is going to be sine equal to sine of 48 degrees over D. And again, I use my given values of 80 degrees and 3 here instead of using the measure of the angle that I found above because this assures more of an accurate response and it makes sure that I'm not carrying errors from previous answers. So solving for D here, I am multiplying these two terms, dividing by sine of 80 degrees. You could have also written this as 3 over sine of 80 degrees is equal to D over sine of 48 degrees because we are solving for D. So then we would have just 3 times sine of 48 degrees and divided by sine of 80 degrees. And this produces 2.26 meters, and we were told to the nearest hundredth of a meter, so 2 decimal points. So the distance from the board to the base of the wall is 2.26 meters. And I can label that up here as well. This is 2.26 meters. And of course, as a practice for you, use cosine law here and confirm that you get the same value. So that's exactly what I was mentioning. So if you do d squared is equal to 3 squared plus, I believe it was 2.4 squared minus 2 times 3, 2.4, and then cosine of 48 degrees. So if you solve for the left-hand side here and then take the square root, you should also get D is equal to 2.26 meters. Now, our next example here. Samira is at an observation deck looking at the view from this city, of the city. She spots a monument 13 kilometers away and another that is 6 kilometers away. From her point of view, the angle between the two monuments is 55 degrees, and we want to know what the distance between the two monuments are. So here, consider she's standing here. This is the monument that's 13 kilometers away. This one is 6 kilometers away, and this angle between if she's looking this way and this way is 55 degrees there. And we want to find this distance here, which is between the two monuments. So here, I have two side lengths and the angle between them. So this is SAS. And when I'm considering can I use sine law or cosine law, I first again look at the angle that I'm given. I don't have this side length opposite to it, so I can't create this ratio here for sine law. So now I know I have to use cosine law, and I'm solving for this side length that's opposite to the 55-degree angle. So that's, remember cosine law, that's the formula for it there. And we define our variable. So this is D here. And D is the distance between the two monuments. So substituting the values we have, we find that D squared is going to be equal to 13 squared plus 6 squared minus 2 times 6 times 13 and cosine of the opposite angle, which is 55 degrees. And here we have 169 plus 36, and this gives me 156 cosine of 55. And if I evaluate this, I get and take the square root, then D is approximately 10.75. And we weren't told to what to round here, Tola. You can leave it as 2 decimal points, or you can round up to 1 decimal point as I did here. So the distance between the two monuments is approximately 10.8 kilometers. And keep in mind, these were kilometers. That's why we have to stay consistent with the unit. So 10.8 kilometers, and that's this distance here. And that is it for this question. We don't have to do anything with these two angles. That's the only value we had to find. So one thing that's also different with application problems of sine law and cosine law is that you may not necessarily be solving for the whole triangle, just the values that you're being asked. And that is something that you have to figure out based on the wording of the word problem is that are you solving for an angle? Are you solving for a side length? And which angle and which side length? Now, in this next example, a hiker walks 4.8 kilometers from the trailhead to a lookout. So, with word problems, start drawing your diagram as you're reading the problem and start filling in all that information that you have. So, here I know I have a trailhead and a lookout. So, here's my trailhead, here's my lookout, and we know that the distance between these is 4.8 kilometers. Then the hiker walks 6.2 kilometers to a campsite. So this is that 6.2 kilometers to a campsite. The direct distance from the campsite back to the trailhead is 7.5 kilometers, and that's why we have that triangle formation. And keep in mind with our trigonometry unit, of course, we want a triangle shape, so that's why we know that this is not going to be going that way because we want to be forming that triangle there. And we're asked to determine the angle at the lookout between the two hiking trails. So consider this as a trail, this as a trail, so we want to find this angle right here. Here we have 3 side lengths and no interior angles, so this straightaway is a clear case of the cosine law. And we're precisely looking for this angle, which is opposite to the 7.5 kilometer side length. So I know that this is the value that I have to start with. So 7.5 squared is going to be equal to 4.8 squared plus 6.2 squared minus double the product of these two and the cosine of theta, which is the angle that we're trying to find. And that's defined here as well. Let theta be the angle between the two hiking trails. So this is theta there. Now rearranging, because we are looking for cosine of theta, we have, I moved this term over here. I moved the 7.5 squared this way. This is the 7.5 squared. And here is that coefficient that I divided through. And if you take and I did some, sorry, minor error there. This should be, because I did the equals 85 degrees there, I should have done is equal to cosine inverse of this whole bracket there, and then that is equal to 85 degrees, because it wouldn't make sense to say the cosine of theta is equal to 85 degrees, or I could have left it at that and then had a next line that was theta is equal to 85 degrees. So the angle between the two hiking trails is 85 degrees. I just rounded to the nearest degree there, and that's this angle here. And you can go an extra step here and label it on your diagram as well. And that is it for this question as well. We don't have to find any of the other angles. Now, and this one is a bit of a challenging problem, but it is very interesting. So I did want to solve it together, just so you see the things that we can do with sine law and cosine law. So here, a regular octagon is inscribed in a circle of radius 15.8 centimeters. And we're asked what is the perimeter to the nearest tenth of a centimeter of the octagon. So let's interpret this first. A regular octagon is made up of 8 identical side lengths. So an octagon, for sure, we know has 8 sides. But a regular polygon is when all the side lengths are the same. So a square is considered a regular quadrilateral because it is a 4-sided shape, which makes it a quadrilateral, and all the side lengths are equal, which makes it regular quadrilateral. A regular triangle would be our isosceles triangle where all the 3 side lengths are the same. Now, in the case of a regular octagon, we know that all of these side lengths are the same. And for for this shape to be inscribed in a circle, it means that it is exactly inside the circle and the vertices are on the circumference of the circle as we see here. Now, this is the origin of our circle, so then we know all of these lines, which are each one on its own is the radius of the circle. And keep in mind, with the radius, I can draw this at any anywhere. I can do this as well. This is a radius. This is a radius. But because I wanted to work around with the octagon shape, I split my octagon into 8 identical isosceles triangles. And the reason why they're isosceles is because all of these legs of these triangles, which are also the radius of the circle, are all equal and they're 15.8 centimeters. So in fact, we also know that these angles are the same because these are isosceles triangles. Oh, and one more here. Now, we don't have enough information to know these, but we do know these angles here. These are all, again, remember, all of these triangles are the same triangle. It's 8 of the same triangle, which means that all of these angles here are 8 of the same angle. And we also know that this interior angle of the circle measures to 360 degrees. Which means to find any one of these angles, we have to divide 360 by 8, which is what we are showing here. And just to avoid confusion, I do label this angle with its vertices. So AOB is equal to 360 degrees divided by 8, which is 45 degrees. So this is 45 degrees, so is this. So is this one, and all of these are 45 degrees. Now, we can actually use this to determine the other angles here. And I want you to take a moment and think how, based on the information we have so far, specifically the fact that these are isosceles triangles. So because these are isosceles triangles, then I know that these two angles, which are the same angle, plus this 45-degree angle, are equal to 180 degree. So let theta be equal to OAB, but that's also equal to OBA. So this angle A and this angle B here. And they're equal to theta, so then 2 theta, because it's 2 times that angle, plus the 45-degree angle there is equal to 180 degrees. And subtracting 45 from 180 and then dividing by 2, I get that theta is equal to 67.5. So and I didn't need to double label that. And just to show you visually as well, I will redraw this. Sorry, that's not the best isosceles. Okay. Let's say that's my isosceles triangle. So this is triangle OAB. So then we have that this is 45. These two side lengths are the same and they're 15.8 centimeter. And these two angles are the same and they are 67.5 degrees each. And now, going back to what did the question even ask me? Because with these problems, you might sometimes get so caught up into analyzing and interpreting the question that you might forget, oh, what was I even looking for? But we were asked to find the perimeter of the octagon to the nearest degree, or the nearest tenth of a centimeter, my bad. So we are looking for these side lengths because there's 8 of these identical side lengths. So really, I am solving for this side length AB here. And now given this triangle, I have two side lengths. I have all the angles, so I can choose either sine law or cosine law to determine this side length AB. So using sine law here, the ratio of AB to its opposite angle, the sine of its opposite angle, which was 45 degrees, is equal to, and these two ratios are the same because it's an isosceles triangle, so it doesn't matter which one I use, but equal to 15.8 over sine of 67.5 degrees. And so AB is going to be this expression here, and it equals 12.09 centimeters. So this over here is 12.09 centimeters, which then going back to our octagon means all of these 8 sides are 12.09 centimeter each. And for me to find the perimeter, I just have to multiply that by 8 or add it 8 times. And so the perimeter is going to be 12.09 times 8, which is approximately 96.72 centimeters. And the reason why I put approximately here, because this itself is an approximation there. So here we can say the perimeter of the octagon is approximately 96.72 centimeters. So this was certainly a complicated question, but again, it's really interesting and just a cool way that you can use sine law and cosine law in geometry problems. And so I hope you did enjoy it and it did make sense. If not, please review it one more time. It does take sometimes a couple of times to review a problem to fully comprehend all the different parts of it, the different components of it. And that was it for our lesson today. That was our last application problem. And please check Google Classroom for any additional tasks, complete the practice problems to get familiarized with different application problems of sine law and cosine law. And as always, don't hesitate to reach out if you have any questions, and I will see you all in our next class.